Hello, everyone. I want to welcome you to my talk today. And in this talk, I'll be discussing how to build Docker images for ARM architectures from CI/CD pipelines. Before I get into that, I'd like to introduce myself. My name is Angel Rivera. I'm a developer advocate for CircleCI. And in my role at CircleCI, I'm engaging the developer community and understanding how they're using technologies, as well as some of the struggles or obstacles they face while implementing or using these technologies. I bring that information back to my team at CircleCI, and we use those learnings to build valuable features for our developers and our customers to ease their lives while developing software. If any of you want to reach out to me after this talk, to discuss the talk or discuss anything in general, you can reach out to me via Twitter. My Twitter handle is @punkdata. So again, if anyone wants to reach out and have a discussion or just to chat, hit me up @punkdata on Twitter. Here are some fun facts about ARM. If you didn't know, ARM stands for Advanced RISC Machines. Although in 1984, when ARM was originated or created in England, it was actually initially named the Acorn RISC Machine. In 1987, ARM became the first commercial RISC processor available. And in 1990, the ARM Ltd company was formed, and that's when the name changed to what it's currently known as, the Advanced RISC Machines processor. And, ARM has been around for quite some time. In 1986, it was powering the Apple II GS, and in 1993, it was also powering the Apple Newton device. So again, it's been around for quite some time, but in recent years, there's been some evolution or innovations made within the ARM architecture. If you didn't know, ARM processors power a lot of smartphones, tablets, Raspberry Pis, and also tons of IoT device and smart devices such as televisions, appliances, and wearables. ARM is pretty much in almost all of the things that we probably use, on mobile devices that we use on a day-to-day. And it's been supported by pretty much all the major operating systems. It's definitely been supported by Linux for quite some time. And I know that for a fact because I've been using Linux for many, many years and always have seen the Linux distributions, right, for ARM, which is pretty cool that, that operating system and that community has always kind of been there to support those ARM architectures. Now, ARM is pretty popular in those, mobile devices and IoT devices, smart devices, because the ARM processor does a great job at processing data while using very low power. So compared to the x86 processors, which are, a bit snappier and faster in certain regards, it still uses way more power than an ARM processor. So, that's why it's kind of a great fit for these mobile devices. Anything battery powered, right? ARM is a great fit for because of this low power consumption, and it's still pretty quick at processing data. So it's a good fit. Now, I want to talk about ARM and implementations of ARM. I kind of gave you examples already about, how it's powering smart devices, smartphones, and all the kind of battery powered devices. So I wanted to share some information about, some of how ARM has kind of been, the innovations within ARM have kind of been applied to a real world use case. So let's talk about IoT sensors. What I'm going to use in my example is a moisture sensor, which is essentially detecting how much moisture is in something. In this case, I'm going to use the example of a moisture sensor in a farm, right? So this is a real world use case where farmers are using moisture sensors to detect how much moisture is in the ground so that they know how much water to apply to their crops. This is a great way for them to kind of be efficient with watering and also helps with their growing process. So if you look at the sensor that I'm showing you in the slide, has a little wire connected probably to a battery, and you can imagine that also has a cellular type device to connect, right, to a cell tower, and then send the data from that moisture sensor back over to some server or some infrastructure that can capture that data and make sense of it. In this case, right, the moisture sensor probably has an ARM processor, but again, it's supposed to be a battery powered device, right? Because you're sitting in a farm, you don't need to have cables everywhere. Also, when you're picking the plants, you don't want to get caught up in any cables. So this is all kind of wireless technology, but the idea is, those sensors should have a long battery life, and the only way to do that is to conserve on things such as processing, and then also chirping or sending that data back to the data center. In recent years, years, this has evolved. The ARM chips have evolved. They've become more powerful. They become more efficient with power. And one of the cool applications that I'm starting to see is, when you have IoT devices sitting in a farm like this, a remote, the farmers or the organizations that are implementing these moisture sensors are now leveraging something called an edge server. And an edge server kind of sits a little bit physically closer to the moisture sensor so that it can capture the information. So it's no longer sending data to a cloud and consuming more battery power. It's actually sending data to a device or some sort of system that's on site next to or very in close proximity to the moisture sensor, and it's not consuming a lot of power. It's also able to process data directly from the sensor in kind of a near real-time situation, and then send a more polished or more refined data set back to the ultimate infrastructure, right, which is maybe some server and some cloud system somewhere. But at the end of the day, these edge services are basically like preprocessors, right? They're taking some information from the moisture sensor and then processing it, maybe doing some kind of even AI on the data, and then sending data up to the final infrastructure that's capturing it. So these are the kind of advancements that are being made, and these edge servers are starting to be powered by ARM processors. And the reason is, number one, the power, right? Consumption. Again, even though you have a device that's processing stuff, it could still use benefit from using a very low power consumption. And the ARM processor does that. The other part to that is the ARM processors are getting faster. So they're able to, process that information just as good as an x86 architecture. So yeah, be on the lookout for kind of these ARM powered edge devices, which are, kind of becoming the norm within IoT type architectures. And it's a pretty interesting time to be, viewing or seeing how this is advancing and the innovations that they're making. So again, right, with the IoT services or device edge devices, they're going to need IoT edge applications, right? So those devices are going to need to run applications that, whenever the data from the sensor comes in, it's going to have to, do some calculations, or maybe even do some sort of, machine learning type situations where it's identifying patterns of watering patterns, right? And then spitting out the best times to water, or any kind of application like that. But at the end of the day, those edge server devices are going to need IoT edge applications to run them on. And what I'm seeing a ton of is these devices are running some form of Kubernetes, right? And that's where if you're running Kubernetes, you're definitely going to have to be running your application inside of a Docker image. And that's where we have to build Docker images that support ARM architectures. And I'll get into that in a few. So another application for ARM architectures or CPUs or processors are for ARM powered servers. Some cloud companies now are actually offering up cloud resources or compute nodes that are ARM powered, right? That means the underlying hardware that hosts your virtual machines are using an ARM processor and also requires you to use an ARM capable kernel. And the reason is because ARM and x86 architectures are not compatible. And the reason for that is they just use different instruction sets, right? So the processors understand their directives in a different way. And that's basically one of the reasons why, you can't use an x86 architecture or kernel or applications with an ARM processor. It will not understand the application, right? Their application is built for a specific instruction set, and you can't mix and match those. So that means, you have to compile your code to whatever architecture you're targeting, because actually the code doesn't really care about where it's operating on, but the hardware actually cares about what kind of software is being compiled and executed on it, right? So the software, if it's built for x86, and again, you're running it on an ARM hardware, it's not going to understand, the processor is not going to understand the software and what it's trying to do. So that also kind of leads into Docker images, that incompatibility, right? So with ARM, you need to be cognizant of when you're building Docker images that you're building to an ARM architecture and not an x86 architecture. So ARM compatible Docker images, right? Again, you need to be cognizant of where you're targeting. And again, if you're targeting an ARM architecture, you obviously need to build for that Docker image for an ARM processor, right? So one of the ways you can easily do that is by implementing, building your Docker images within CI/CD pipelines. That streamlines the process. The problem is a lot of the current CI/CD providers don't have ARM building capabilities or ARM capabilities to build your software. They don't have the hosts in the runtime to build your software. But you're in luck. CircleCI has actually recently released that ARM resources. So we now have the ability for people to leverage ARM in their CI/CD pipeline. So you can build your application to an x86 platform, or if you choose to, you can also build it for an ARM architecture. And the way we did that is providing what we call resource classes, which again are ARM capable underlying hardware, right, where you're running your code. So with that addition of the ARM resource classes, we're able to allow developers to build their applications, compile them for ARM, right? And they also can build Docker images that support the ARM architecture. And that'll give a nice, clean ARM feel across the board. So you can test your applications in ARM. You can run your code on an ARM hardware or ARM processor, and know that the applications, the Docker images, and anything you build on that platform, the ARM platforms within your CI/CD pipeline, are going to function in whatever ARM architecture you're targeting, which in this case could be a Kubernetes cluster. So in this demonstration, I'm going to go and show you how you can implement a CI/CD pipeline within CircleCI that actually builds, tests, and deploys an ARM-capable Docker image to a newly created infrastructure. So let's get started with our demonstration. What I have here, what I'm showing you here is the code example that I'm going to use for my demonstration. Essentially what it is a simple static Node.js application. It just renders a page. And this will be, any code changes will trigger our CI/CD pipeline that will do a couple things. So let's take a look at the CI/CD pipeline. I'm going to jump into just the building the Docker image portion of this pipeline, or the job, which is listed right here. As you can see, I have a job named build ARM Docker image. And essentially what I'm going to do here is build a Docker image that is built on an ARM compute node or executor on the CircleCI platform, as well as create a new Docker image from this application and the changes made to the application for deploying to an Elastic container service on AWS. And the container service will also use Pulumi to be provisioned, right? So Pulumi will create all this infrastructure, and it will also deploy this Docker image to this newly created uh, Elastic Container Service cluster. And by the way, the cluster will also be powered by AWS Graviton 2 ARM compute nodes. So it's kind of an ARM end-to-end ARM experience with the CI/CD pipeline. So let's get started. I'm just going to quickly cover the main thing that you need to leverage an ARM executor, and it's just these quick keys here, which are essentially, the machine, which tells the platform to execute or to give you an executor of machine type, which is a virtual machine. And then the resource class is actually where you define what kind of executor you want to use. In this case, we want to use ARM, so we would put the value of ARM.medium or large or whatever capacity compute node you want. I'm just going to use medium here. And then finally, let's jump over to the main point, though. One of the main points here is that in order for you to build a Docker image that will be ARM capable, you have to inherit from the Docker image base, right? So Docker works as with inheritance. It inherits its capabilities from a previous image. In this case, we're going to use the ARM64 v8 version and with a node image, right? So this line right here is essential in your Docker file to create a ARM capable Docker image for whatever service you're going to deploy to. Now, let's show you how we're going to, trigger a pipeline. So basically, we got to change some code, and I want to add just a quick message here, node server running, and then I'm just going to add, some dots or whatever. Then I'm going to save it, and I'm just going to go through my regular flow, right? Like, I don't know, let's see, trigger build, right, as a commit message, just to speed things along. And then what we're going to do is, we forgot to update that. So we're going to say, just call it trigger, right? Another message. We'll do 2 pushes or 2 commits. And then we're going to push this upstream. So once we have that pushed upstream, we're going to jump over to our Circle CI dashboard, which has detected my code changes, and it's going to run all the jobs defined in my config.yaml file. Now, we'll get into the details of this after things have run and been provisioned. So our Docker image job has completed, and the Docker has been pushed to Docker Hub. Let's check on our Pulumi provisioning process. So Pulumi is an infrastructure as code system that enables developers and operators to basically build their architectures and other cloud resources using code, right? So you can define all of those things using code. In this example, I'm using Python, and what I'm creating here is an AWS Elastic Container Service powered by AWS Graviton 2 ARM compute nodes. And then I'm also, creating things like security groups, VPCs, all from scratch, right? So the idea here is to build a pipeline that will test my application in the environments that I'm targeting for deployment. In this case, it's an ECS cluster powered by ARM compute nodes. So our Pulumi application has provisioned and deployed our application to the ECS cluster that it created. And we can test that the application is actually functioning on that cluster live by just, copy and pasting the URL that was created. And then we'll just show that to you here. The application is running in an ECS cluster. If you want to take a look at that, we can show you that the cluster was created here. It's called App ARM. And as you can see here, it's got pretty much a service running. Here's some EC2 instances. So it's a 3-node cluster. And what I'm going to show you real quick is the fact that it's running on a Graviton 2 ARM compute node, which is this designator here, T4G. The G at the end, of this initial designator or compute node type signifies that it's a Graviton 2 ARM compute node. So again, right, like this cluster is powered by ARM. The Docker images is built for ARM, And the pipeline itself, if you want to take a look at that, actually does what I call a smoke test. So as you can see, right, it did all of these things, built a Docker image, created and deployed this Pulumi infrastructure. It also performed a smoke test, meaning it was the application deployed, and is it functioning the way we designed it to function. In this case, it's a simple test that's just checking for an OK200, which is responding, and we verified it manually. But you can imagine, as a developer, you're working in your flow, and you don't want to stop to check if your app is running and then you continue on. What you do is you build a pipeline like this, and then it'll automatically go through the process, smoke test, and then right now I put it in a manual job, is what we call it. And the reason why I put that here is for this demo, so I could show you, you can do things like manual jobs if you actually want to verify that it's running. But normally what I do is I just don't have this approved job step here, because what happens is once it's, smoke test pass, it'll just go ahead and destroy that cluster. And I just click that button in order for the next step of my pipeline, which is to destroy all that awesome infrastructure we built using Pulumi. So that's basically it in a nutshell. If anyone wants to reach out to me to ask questions or get further details on this demonstration, just hit me up at punkdata on Twitter. And I want to thank you all for attending this talk. Right, I almost forgot. I'd appreciate any feedback, if at all possible, from you. If you could just use the URL that's on the screen, and send me some feedback, constructive criticism on how I could make this talk a little bit more informative or more exciting, or just better it all the way around. I'd appreciate that. Again, thank you, and have a great event.